I'm Will Allen from Mercersburg Academy, and for my Makers Lab Senior Springboard project, I made an induction furnace. This is a device that utilizes electromagnetic properties to heat and melt metal for both industrial and artisanal purposes, like jewelry making or automotive manufacturing. Outside of school, I've had an interest in metalwork for quite a while, mostly using a trial and error method, gathering tools and techniques little by little. Here are two of my recent pieces: an aluminum ear with brass piercings and a Damascus knife. When I was deciding what I wanted my final project to be, I knew I wanted it related to metalwork. I began thinking of one of my most important tools, my charcoal forge that I used to heat my metals. Burning superheated charcoal was hazardous, sending sparks everywhere, and it also didn't yield a consistent heating of my materials. I knew making any type of forge or furnace wouldn't be an easy task, but Maker's Lab provided me with the opportunity to make a new one. I went to YouTube to find new heating techniques, and I immediately became interested in making an electrically powered furnace because I wanted to expose myself to electronics. I researched electric kilns and even scaled down industrial arc furnaces, but they seemed either too dangerous or too time consuming. It was seeming hopeless until I came across a video by the YouTuber The Backyard Scientist, who gives direction on a personal induction furnace's construction. After researching this unique method of heating, I saw it as the most viable option for my new furnace, even before learning it would be a great project. Induction furnaces are more efficient, safer, and easier to use than conventional combustion heating and most other forms of electrical heating. The term conventional heating describes combustion-based heating that we are all used to. Take cooking with a gas oven, for example. This multi-step process begins with burning gas to produce heat. This heat warms the oven, and the oven cooks your food. A blacksmith's forge works similarly, where a fuel is burned to heat an area that workpieces are placed within to heat up. Within every step, there is a loss of heat. Induction furnaces do not have this loss because the only thing generating heat is the workpiece itself. This makes it non-conventional because it relies on metal's interaction with magnetic fields produced within the coil instead of combustion or heat transfer. When you run electricity through a copper wire, it makes a magnetic field around that wire. This is because copper is a conductor, and all conductors share this property. Induction is where the magnetic field from one wire can generate electricity in another separate wire. Induction furnaces operate on this principle, but instead of generating electric current, they generate heat in the second isolated wire because of a particular magnetic field called an eddy current. Imagine eddy currents as their name suggests. As a vortex of water, people using this device stick the conductive piece, the arrow, into the position with the highest resistance, perpendicular to the flow. This electromagnetic resistance excites the electrons, causing the material to heat up. This main function is achieved with only two components in the assembly: the board, including the coil, and the power supply. The board is a relatively simple circuit that outputs regulated power to the coil to produce eddy currents. The power supply powers the board. So, wiring them all together completes the very basic function of the induction furnace. Everything else in my assembly is for cooling and regulation to make handling safe and to increase the longevity of the device. For example, the coil doesn't get hot when the device is turned on, but the residual heat coming off the workpiece can make it too hot to touch. So I installed a water cooling system to cool off the coil while I work and to cool it down even faster when it's no longer in use. The small display screen is a component that I use to monitor the amount of power flowing to the board, protecting it from being overpowered. Much of my labor actually went into the housing assembly because I wanted to fit everything together cleanly. I used metal from broken microwaves I scrapped from the Mercersburg Electronics Recycling with the help of my roommate Ollie, and an old duct fan I had at home. This project did come with some difficulties, the largest error being the destruction of my first power supply. This happened because I purchased a power supply underrated for the task at hand, and during some of my preliminary tests, I've fried some of its internal components. But I looked at this as an opportunity to upgrade the device's potential. My current power supply is now much more powerful and reliable. What I would have done differently was really research the qualities I had needed for my first power supply, instead of focusing on the cheapest option that met the minimum qualifications. I should have been searching for the most reliable option. I am extremely grateful for the opportunity to complete this project, and I'm really pleased with how it turned out. I learned to work with abstract qualities of electromagnetism and actually made a machine that I will use. I allotted a lot of time to this project both in and out of school because I was lucky enough to have the tools at home to complete the project. Here's an example of it in action. I'd stuck a railroad spike for about 2 minutes in the coil to heat it up. At the moment, the temperature record stands at about 1,600 degrees Fahrenheit, which is 871 degrees Celsius, capably melting aluminum for pouring and casting in molds, creating charms like this one. I suspect it will get even hotter as I figure out the specificities of the furnace. Building on this, if I had more time, I would add a reservoir to the cooling system so that I could run it for even longer with no fear of overheating. I would also add insulation to some parts of the device to keep it even more protected from residual heat. I'm not claiming to be an electrical engineer, nor that my explanations of how this device functions are that accurate. I completed this project with safe practice and a basic understanding of electricity, but it did help to be stuck in quarantine with a BS in electrical engineering. My dad, Bill Allen. I could not have wired 240 volts from our home's fuse box without his assistance and safety advice. Thank you for watching.